One-to-one functions. What do you think one-to-one means? Was that? Yes, you read that from the paper. I saw you reading it. Yes, that's exactly what it means. Instead of writing one-to-one, we can use symbols like this. That means one-to-one. It makes it a lot easier to use a shortcut. That means one-to-one. Okay, now what it means one input to one output. Yes, that's pretty much what it means. In terms of a machine, that's what it means. In mathematics, the input functions are our independent variables, which is our x value. The output is the dependent variable, which is the y. If you think about it, you can't tell me what y equals until you define x. X can be anything you want it to be, hence independent. That's the input. You plug it in there, let's say x equals 2, we defined it, we plug it in there, and we have a value for y. That's our output. Now, we have a couple of ways of looking at this, called mappings, one of them. You have your x values and your y values. For every x value you plug in there, if each of your inputs, each of your x values results in one and only one solution, that's one-to-one. Give me an example of something that would not be one-to-one. Yeah, if A went to 2 as well. If A went to 2 places, then it wouldn't be one-to-one. Then we couldn't use that anymore. And we call those relationships. We talked about this earlier in the semester. Correspondence and a relationship. Ever hear those words? Correspondence is what we used to describe when people sent out mail or letters to each other. You're communicating by correspondence. If I sent out a letter to you, could I send the same letter to somebody else? No, unless you lived in the same house. So in other words, if I sent a letter, it has to be a different letter to a different person. That's correspondence. A relationship is how they, so think of a relationship, boyfriend, girlfriend. If it's a relationship, then it's one-to-one. And unless you're in America, then it's many to many. But this is what we're looking for. Now, why is this important? Why is one-to-one important? You can predict that, yes. But even more so than that, it has to do with the graph and the shape and the relationship of the graph. But if a function is one-to-one, that means for every x value you put in there, it only maps to one y value. that means that an inverse exists. If a function is 1-to-1, then it has an inverse. What's an inverse? That's reciprocal. But yeah, I see how you, I would think that. No, but we'll go into further definitions here with that. So let me look at the other ways that would define 1-to-1. Here's a set of numbers. Are these points 1-to-1? Why not? There's what?
There's two of the same X.
Yes, there's two same X values, but they have different Y values. It's not 1-to-1. So if you have the same X's, you have to have the same Y's. If you have all different X's, then it's automatically 1-to-1. In other words, I can have a set that looks like this. Is that 1-to-1? Yes, it is. Because for each X, it points to one and only one Y value. There are no duplicate X's. Let's look how it looks graphically. If we took this first and graphed it, we'd have 1, 2, we have that point. We have that point. 2, 1, and then 1, 3. Remember we talked about earlier the vertical line test? So a function cannot fail the vertical line test, because for each X value, there has to be one and only one Y value. So that's important. So if you have two different X's, the same X is two different Y's, then it's not a function. So we can't use it. So it cannot be 1-to-1. But if we had these points, they all pass the vertical line test. They're all functions. They,
Any functional.
yes. Because give me an example of something that's not a function. Well, a picture, that's not a function. Circle, exactly. That's not a function. It fails the vertical line test, it's not a function. In other words, at this X, you have two values of Y. So yes, that's an example, perfect example. Now, so how to find an inverse of function? Well, we have to have, first off, we have to have a way of distinguishing. We have a function. It equals some value of Y. How would we differentiate the inverse function? That symbol there, the -1 exponent, tells us that that's an inverse. It doesn't mean 1/f of x, because that's what the negative exponent tells us. It's a reciprocal. When we deal with inverses, that's its own symbol there. That's very important. So it only has two steps. First step, switch X and Y. Then solve for Y. That Y will then be your inverse. Okay, you also, well, back over here. You also see in your sheet examples of one-to-one. This is one-to-one. This is also one-to-one. Because for each one of these inputs, they all go to only one output. This is one-to-one. This is one-to-one. This is not one-to-one. In other words, each X can only have one arrow out of it. Is this one-to-one? Yes, it is. Yes, it is. So, because this is how we find, so let's look at this example here for our first one. Let's say Y is equal to 3X plus 2. Find its inverse. So what's the first step? You switch X and Y. Step 2, solve for Y. How do we know that the inverse would exist? Because of this function. Is it one-to-one? Why? How do you know that? It's a linear, exactly. That's exactly all you need to know. It crosses at 2, up 3, over 1. Because it's a linear function, it's automatically one-to-one. How about this one? No? Why?
Oh, no. It's a, it's a quadratic function.
So it looks like what? And it goes up 4.
It's not one to one.
I know, why not?
We'll have to do the horizontal line.
We haven't talked about the horizontal yet, so we can't talk about that.
Because two axes that don't have the same.
How do you know that?
On the x-axis, on the y-axis.
It's reflected across, yes, this is squared, no matter what you put in there, it'll become positive. So if I put -2 in there, or if I put +2 in there, it'll give me the same answer. Yes, so because of the symmetry of a quadratic equation, it doesn't satisfy the one-to-one test for our inverse functions.
So it's not all-
Right. Because of this. Well, let's see what won't happen when we try to solve this. If we try to solve this, remember, first step is switch X and Y. Then what? Subtract 4. And then you square root. But the rule says whenever you square root something that's squared, you have to put a plus or minus in front of the answer. So there's what the problem you have. This, what this graph would look like is like this. Right. Now, because we look at the symmetry of an object, because even powered functions are obviously not going to pass the inverse test. How about cubic functions? At some point. But remember, they also have this. It is a function, but is it one-to-one? Because now if we were to take the inverse of this, the graph would look something like this. And therefore it fails, it's not a function anymore. Which is what we use now called the horizontal line test, because we use the vertical line test test for a function. If you draw a vertical line, it only crosses once, then it's a function. Now, with the horizontal line test, this is to test for an inverse. If you think about it, the difference between a inverse and a regular function, or let's look at this, that's a regular function. We switch X and Y. So if I gave you these points here, this is Y, what would be my inverse? Right. Like the first step said, switch X and Y. That's all you have to do if you're given points. What does this do to the graph? Well, let's see. It flips around where?
Right there.
A little bit of both, actually. So we have 1, 3 becomes 3, 1. 2, 5 becomes 5, 2. And then 4, 7 becomes 7, 4. Now, what's really happening is there's a switch around about that line, y equals x. So if we had our radical, we'd flip those. It would look like that. So it flips across the y equals x axis, the diagonal. And that's really what's supposed to be happening with these guys. But my graph is horrible. Which is why we flip x and y. It's diagonal, it's a diagonal line that's symmetric about.
So without solving it and like flipping the x and y, couldn't you just use that horizontal line test to see if it's 1 to 1 on the graph?
Well, you just said if like the x squared, it passes the vertical line test, but fails the horizontal line test.
So
It's not 1 to 1, right? If it fails the horizontal line test, it's not 1 to 1.
but it is.
It is a function, right? Yes. I know, so it gets kind of complicated the more you think about it. Let's see some examples we have here. Example 3. Oh. Let's look at example 3. Oh. Or example 1 and 2. Yeah, that's boring. Well, we could do example 1 if you wanted to. Determine if it's 1 to 1. Oh, let's look at example 2 first. A. Determine whether it's 1 to 1. We're not asking about inverses yet. Is it 1 to 1? For every x, is there a one value of y? For every x, there's only one value of y. Yeah, right here. There's only one value of y. We're not talking about the horizontal line test yet. This is still pretty much the vertical line test. This is 1 to 1. For every x, there's one and only one value of y. How about the cubic function? Is that 1 to 1? For every x, there's only one value of y, right? For example, example 3 now. So that's what you're looking for. There's a difference between the horizontal and vertical line test. The vertical line test tests if it's a function. 1 to 1-ness asks, is there one value of x to one value of y? One input to one output? Yes. Don't get those two mixed up. Because now eventually we'll talk about, is there an inverse? That's when we have to look at the horizontal line test. So there's this one here, the x squared would not have an inverse because it fails the horizontal line test. So it has no inverse. The cubic function, it passes the horizontal line test, so it does have an inverse, a unique inverse. Okay. 1, 2, 3. 2, 3. So we have at 2, -1. -1, 0. And at 2, 1. This example says, show a one-to-one function, draw the graph of its inverse. We know it's going to have an inverse because it satisfies the horizontal line test. So what would the inverse look like? Switching the XY coordinates. So in other words, from -2, -1, it would become -1, -2. That's the first point. This is Y, this is inverse. -1, 0 becomes 0, -1. 2, 1 becomes 1, 2. We just simply plot those points. So at -1, -2. At 0, -1, and at 1, 2. So there is the inverse. Again, it's symmetric about the line y equals x. Yeah, so that's the easiest way. If you're given a graph, just switch the x and y values like this and then plot the points. Connect the dots. So yes, that's what I said. To answer your question, is it a rotation? Is it a flip? Yes. It's a little bit of both. Let's try radical or rational functions. Verify the inverse. Now, because the graphs of functions and their inverse functions are symmetric about the line y equals x, to prove or show that inverse of y we use compound functions. In other words, if we take the f of f inverse of x, in other words, that's what this is, it should come out as just x itself, the variable x. Or if we take the compound function f inverse of f, it should still be x. Okay, now what does all this stuff mean? Remember doing in composite functions? F of G, G of F? That's what we're doing here. So f of x is x cubed. F inverse of x is cube root of x. Do the composite function of both of those. Okay, composite. Do the composite of these. So we'll have f of f inverse of x. That means this goes inside here. What does that equal? The cube and cube root cancel. We have x. That's check. Then you have to check the other direction. Put the original function inside the inverse. So the original function is that. Put this inside of here. And they cancel. So that shows that f and f inverses are inverses of each other. That's how you prove it. Let's prove that these are inverses of each other. The same way. Are they inverses? So we take this equation, plug it in place of x. Plus 3. The 2's cancel. So we have x minus 3 plus 3. The 3's cancel. X. That one works. So now we take this equation, plug it in place of x there. 2x plus 3 minus 3. So it works. So that's how you check to see if an inverse is really the inverse. If you do the composite functions and we get x as a final solution, then that's proof. Anything else, it doesn't, that means it's not right. Find me the inverse of that one and prove to me that it's a right inverse. So what's the first thing I do? So I have x equals 1 over y minus 1. Second step, how?
Multiply by
We have to multiply. Or actually, there's nothing we could have done. We could have reciprocated. That's a lot of work. What we could have done is just flip this is over 1. Because the next thing we would do here, we divide by x. So we'd have y minus 1 equals the x's cancel is 1 over x, same thing there. Then add 1. So there's our inverse. What's that?
oh,
Yeah, I just went in and flipped it, because if I didn't, if I cross multiply by the y's, these cancel. Then I divide by x, I get 1 over x over here, so I get the same thing. Now we have to do the composite functions. Let's take this, put it in place of there. So we get 1 over 1 x minus 1. So this is a fraction over a fraction times the flip of the bottom. So it's x minus 1 plus 1. That one works. And then we take this equation, put it in place of there. These cancel. So it's a fraction over a fraction. So they're inverses. You think that one's hard? Wait till the next one I give you. That'll be example number 7. Did everybody follow what we did here? The part that a lot of people forget is when you have a fraction over a fraction, what do you do there? So you just reciprocate the bottom and multiply to the top. All right, example number 7. Y equals 2x plus 1, x minus 1, where x cannot equal 1. Find the inverse of the function and check your result. The first step's easy. Two y plus 1. So what do you do next? Yeah, cross multiply, get rid of the denominator here. So we have x times y minus 1. Then what? You could, but you still have y's on both sides. Let's get rid of the parentheses.
Y minus x.
Yeah, you could, but that would still leave you separated from there. Because now we have the Ys by themselves. We can now move them all to one side. So let's move this Y over here and this X over there. So we have XY minus 2Y. I subtracted 2Y from both sides. And I add X to both sides. So far, so good. To get the Y by itself, I factor it out. And then I divide by X minus 2. So my inverse is 1 plus X, X minus 2. Did we get that? Or close to it? Where'd you? Half the class said yes, half is no. So where did it mess up? This part here, the factoring part?
I, what I said, I took away one first before distributing the X.
You could do that. So you still get the XY minus X minus 1.
Oh, then I guess I did.
Oop. But then you have to put the Y's to one side and then. So now we know we have this. Now we gotta do the composite functions. Take this equation, put it in place of X. And then that page. So. That equals 1 plus 2x plus 1 over x minus 1 over x minus 2. Oop, nope, that's an x. This whole thing here goes there. So it's 2x plus 1 over x minus 1 minus 2. Then what do? If you multiply the top and bottom by the LCD, which is x minus 1, or it's take both of those, multiply by x minus 1, it'll simplify the whole top and bottom part. So it's x minus 1. These cancel, so it's 2x plus 1. This to this, the x's cancel, so it's 2x plus 1 minus 2x minus 1. Let's multiply each of these terms by that. The ones cancel, so we have 3x. Two x plus 1 minus 2x plus 2. The 2x's cancel. So that one works. Now we got to do the y inverse. So anywhere I see an x here, I put that. 1 plus x, x minus 2, plus 1. 1 plus x, x minus 2, minus 1. Do the same thing there. The LCD is x minus 2. And multiply every term by x minus 2. Those cancel, so we have 2, 1 plus x, plus x minus 2. 1 plus x minus 1 times x minus 2. Two plus 2x plus x minus 2. 1 plus x minus x plus 2. The 2, negative 2, x, negative x. So we have 3x over 3. So it works. Those are inverses. Yes. Yes, these were not easy. Again, it's all algebra. And to be honest with you, when you get calculus, this is the part you'll have trouble with also there, the algebra part. Any questions about that one? Anybody have any trouble finding the inverse? So finding the inverse is easy. It's checking the inverse. So you could you could just roll the dice and say it's inverse. It'll work.
So one of them is taking the original equation. Putting it in the function, check it,
Right.
and the other one is taking the inverse, you think, which-
Yes.
Yeah.
To both sides have to be true because there may be situations where one works, one doesn't work.
You feel like doing all this, but also graphically figured out, right?
Yeah. But it's a little more work. With that, that's what example 8's about. Example 8 says you have a function f of x equals x squared, but the only x's I want are x greater than or equals 0. Graph f of x and f inverse of x. Yeah, you're right. There are many ways you could do it. Yes, you could graph it, plot the points and just switch the x and y points, and that'll give you the inverse. Yes, that's what you did. Or we could find the inverse, and then you'll see how easy the graphs are going to be. So you don't have to do the flip of the x and y's. What's the inverse going to be?
It's the second rounding. Right, just because I know what it looks like already.
The sideways prep, yes. This,
Half the sideways graph.
yeah,
Yeah.
it's rotated, it's flipped. Yeah, so here, if you see that, then we just change. And we square root it. So we have y equals square root of x. We only want the positive X values. So what does this graph look like? Right, so at 0, it's 0. At 1, it's 1. At 2, it's 4. And it goes on forever. This graph starts at 0. At 1, it's 1. At 4, it's 2. And it looks like this. Again, it's symmetric about the line y equals x.
Why was it not the left half of it?
Because.
Because it's only X greater than 0.
Yes.
Yeah, but yeah, our we want to limit it to that. Because if we did the whole thing, then it wouldn't be a function. There's the horizontal.
Um,
Yes. And this is what this section talks about is you can now limit the domains you're dealing with. So the hardest part about this, finding the inverses, deals with if you have rational expressions, simplifying those. Those seem like those most difficult ones, the fraction ones. Other than that, again, if you know if graphing works better for you, you can always do that. Unless it wants the function itself. So what do y'all think? About inverses and functions? Difficult, easy? It's yeah, it's the algebra, it's the algebra, the mechanics of the algebra that makes it difficult. And once you see it, everybody goes, if you had trouble with it, you say, oh, that's easy, I can do that. All right. That does it for that. I think it does it for that chapter too.